Assalamualaikum warahmatullahi wabarakatuh. For today, I'm going to explain about Chapter 8, MIPS branch and arrays. Including this chapter, I will also continue from the previous lecture about addressing mode, the fourth and the fifth addressing mode in MIPS branch and jump. In assembly language, control structures work by changing the normal order in which instructions run. There are two types of transfer of control. One is conditional and then another one is unconditional. Conditional will occur when the transfer might or might not take the place, depending on the current state of the program. Means if it's false or if it's true, does it need to take the branch or not? In assembly language, a conditional transfer is executed using a branch instruction. An unconditional transfer always occurs regardless of the program state, meaning there is no condition to test. They would just transfer or jump to the instruction. So in assembly language, this is achieved using a jump instruction. Selection structures like if statements use a forward jump. On this figure, okay, forward jump from the top sequentially. Usually we need to execute sequentially, but this time a forward jump is jump down to a certain higher memory address. Iteration structures such as loops use a backward jump to an earliest instruction, which is the lower memory address, to repeat that instruction. Branching. Program counter normally increments by 4 after each instruction. The program counter will point to the next instruction in the memory. The branch instruction modify the program counter, which allow the processor to skip sections of code or repeat the sections of code in this case of loops. The basis of decision making is determined by the input data and the values generated during computation. This would lead to the execution of different instructions. In a high-level construct, we use the if statement, but in the assembly code, they often implemented using if with goto and labels. In MIPS assembly implementation, two decision-making instructions act like if plus goto. So these are known as conditional branch instructions. There are two basic conditional branch instruction. One, branch if equal or BEQ, where the syntax is that BEQ RSRT and then label to jump. For example, branch equal T1, T2, and then branch to exit. So this instruction means that jump or go to this label if the content inside the RS is equal to the content inside the RT. Okay, so in the example we use, go to exit if T1 is equal to T2. The mnemonic that we use, BEQ, is equal to branch if equal. The second one is branch not equal, where the syntax BNE RSRT label means go to this label if the content inside the RS is not equal to the content inside RT. For example, BNE a branch not equal if the content not equal to the T1, then branch to else. Okay, so we will use the mnemonic B and E. Example 1. In the C++ statement, if A is equal to B, then we will execute B is equal to B plus A. Else, okay, not else, then they would execute B is equal to B plus A. However, if A is not equal to B means it is a false statement. It will skip the B is equal to B plus A and execute B is equal to B plus 1. You can see on the flowchart Okay, if the statement is true, then there's an extra statement that they need to execute. But if the statement is false or no, then they need to only execute one statement. B is equal to B plus 1. In the MIPS instruction, when you translate A is equal to B, we will use the opposite. Use the opposite to get the same structure. As you can see now, if S0 is not equal to S1, means A is not equal to B, then we would execute B is equal to B plus 1. So in this case, label 1. So if S0 not equal to S1, the branch will be taken, means they will jump to this label, branch to this label, means this next instruction, if B and E result is true, because S0 is not equal to S1, then we need to execute this statement, ADDI S1 S11, which is equivalent to B is equal to B plus 1. Now, if S0 is equal to S1, then they would ignore this branch. Okay, the branch will not be taken, and the next instruction will be executed, which means this line 6 add S1, S0, S1, which is the next the instruction for the true statement, B is equal to B plus A. And then the instruction B is equal to B plus 1, which is ADDI S1, S11, will be executed after that. See? Now, if you want to get the same structure as the C++ statement, the key component is that reverse, okay, do the opposite operation on the C++ statement. So in this case, not equal. Then you will have the same structure. Now look at the same, another example too, that using if else. If A is equal to B, then B is equal to B plus A. Else, do another false statement, B is equal to B minus A. And then continue with the false statement, continue with the main function, main statement, B is equal to B plus 1. Okay, regardless if it's true or false, the last statement will be executed, right? Now, as I have mentioned before, if it's equal in the C++, then do the opposite. Branch not equal. S0 branch to else if the statement is true, means if S0 is not equal to S1, then we will jump to the else statement here, where they will execute B is equal to B minus 1, B minus A. So S1, S0, S1. So S0 minus S1 and then store back inside S1. And then after that, continue with the next instruction, regardless if the branch was taken or not. Here, B is equal to B plus 1. Okay, but let's say branch not equal is false. S0 is equal to S1. Here, A is equal to B. Then execute line here, line 6. Okay, add S1, S0, S1. And then jump exit. Here, we use unconditional branch to jump to label exit because we want to skip the no here, the else statement here. So we don't want to execute the next line. Okay, if you miss the J exit, you would execute the else statement here, sub S1, S0, S1. So in order to skip this else, we need another label exit that will execute B is equal to B plus 1. Okay, so this jump will go to the line 9 and execute ADDI S1 S11, which is B is equal to B plus 1. So we can see that regardless if the branch is taken or not, the statement ADDI here will be executed. Now you understand, right? how to do this if-else statement. Another example is use a multiple condition. If A is equal to B and A is equal to C, then if the statement is both true, then we will execute A plus plus, else B minus minus. And then after that, we execute B is equal to A plus C. So here, first we test A is equal to B. Okay, if it's yes, we test another one. But if it's false, we go to the B minus minus, right? So it will go to else automatically. So if the first one is false, we automatically jump to B minus minus here. Okay. Now, and then the last one after the B minus minus and A plus plus, we will execute this statement. Okay. So S0 is A, S1 is B, and then S2 is C. Okay, for the first statement, A is equal to B, we use the opposite, branch not equal S1 and S2. Okay, so if this first statement is true, means they are not equal, which they need to go to the else statement, right? So we jump to else. Okay, and they would execute ADDI S2 S21. Okay, so if first statement is true, okay, straight away branch to else. Now next one, let's say S1 is equal to S2, means A is equal to B. Now they will need to test again if it's false, because we, as I mentioned before, use the opposite. So if it's false, we go to the else. So if the second statement is also true, means not equal, then we branch to else, right? Okay, so execute the statement if branch is taken, regardless from the first line 6 or the line 7. Okay, what if S1 and S2 is true, and then we test again S1 and S3 is also uh, true, means that they are equal. Okay, so both of them, S1 A is equal to B, and also A is equal to C. Now we add one. Okay, we will execute this statement. Okay, if statement is false, means that the branch is not taken, right? Now, and then, because we don't want to execute the B minus minus here, the else statement here, now you need to use the jump next, the unconditional branch. So they will jump to the label next here to exit from the if else statement. As for the else statement here, there is no jump next because the processor will look for the next line. In this case, if you are under the line 10 and you are executing it, then the next line will be executed after that. So the jump next was not needed for the else. Okay, they only be needed for this statement. Okay, for the first one statement. Okay, next, loop instruction. Loops execute a block of code repeatedly based on a condition. For loops and while loops are common constructs used in high-level languages. So both for and while loops repeatedly execute a block of code until a condition is not met. Means we would repeatedly run the loops until a condition is not met, means the condition or the statement is false, then you can exit from that loop. So you need a condition to make sure that the condition is not met, then you will not be in a repetitively groups. Okay, so here you can see integer I is equal to 0 while I is less than 10. And then we will add I is equal to I plus 1. So this would be repeated 10 times. I is equal to 1, I plus 1, I plus 1, 10 times. 10 times, all right? They will repeat back again and test this. Is I is less than 10. So at the first one, I is 1. And then test again 2, 3, 4, until I is equal to 10. Now, is 10 less than 10? No. So it will be N. For the MIPS, we will use T0 as I, T1 is 10 as a sentinel or condition evaluation, and then T2 is 1 for comparison. In the case of your chapter chapter files, T2 here is not needed here. Okay, so there's a little bit changes in the coding on line 10. Okay, so look at the first version. Okay, in the text segment, I put a declaration for I, T0, register 0 and add with 0. Okay, ADDI T0, register 0 and 0. So we will have T0 is equal to 0 here. And then we put a T1 as 10. So ADDI T1 0 10. Now to test the condition, if I is less than 10, so we will use set less than S0 T0 and then T1. Okay, so in this case, S0 here will hold the flag. It will hold the flag if it's true or false. True will be 1, false will become 0. So here 0 is less than 10. So it will be true, right? So S0 will become 1. So 1 here will be tested. S0 will be tested. BEQ. If S0 equal to 0. Okay. So if it's 0 means that equal, right? So means that um it uh equal means false. Okay, because S0 contains 0 means if it's false, here you will end the loop. All right, so at the moment it was not end because S0 is 1, so 1 is not equal to 0, so we will not take the branch and continue with the next instruction. Line 11, ADDI T0 T01 means I is equal to I plus 1, and then repeat back again to the top. Okay, at the testing, I is it I less than 10, right? So we will jump to while. So for this line, they would jump to this statement. Okay, here if I is equal to 10 and then S0 is equal to 1, else, okay, because I is not 10 yet, so S0 become 1 lah. Okay, now at this moment, okay, here, okay, add I, okay, plus 1, okay, I is equal to plus 1 and then jump while. So as you can see, they will repeat this instruction. And then again, this will be tested. Okay, because I is equal to 1 now. Is 1 is less than 10? Yes, true. So S0 will become 1. So 1, is it equal to 0? No. So we continue again. So this will be repeated until T0 is equal to 10. So when they check, T0 is 10, which is I is equal to 10. Is it 10 less than 10? Now, this one become false. S0 will contain 0. Okay. Now, BEQ, 0. Is it equal to register 0, which is always 0? Yes. Now, they would branch to N. So, this is how we use the loop. Okay, we write the command in assembly code, okay, using the MIPS code. Alright. Now, another version is that we use command BGT. BGT is a pseudo instruction. It's a pseudo instruction. Now, here we will use BGT, branch greater than, is T0, okay, greater than T1. Okay, so in this case, we will check, okay, if, please correct this command. Okay, now, if I is less than 10, okay, now it should be yes. It should be yes. Okay, it should be yes. And then I is equal to I plus 1 and then go back up, right? Now, but this time we are using a BGT, means we want to reverse. We want to reverse it. So this time, okay, I would erase this. Okay, now this time they want to make it if I is bigger than 10. Okay. Now, if I is bigger than 10, yes, okay, so then they will end. But actually, it's not. In the C++, it was not true like this, right? So it's supposed to be, you need to correct this as yes, and then this is no lah. Okay. Now, remember when I said, if the statement is less than, then you need to use the opposite. Thus, BGT is actually greater than, right? Now, some of the student will use a branch greater equal. Yes, true. So, branch greater equal, then if T0 is supposed to be greater equal, so it should be equal because the opposite of less than should be greater equal. So it should be BGE, yeah. Okay. Now, if you use a BGE, then the calculation will be corrected. Right. Now, if you are using a BGE, if a 0 is greater than T1, then we need to branch to N. But it's not because T0 is 0. 0 is less than 10, which is false. So we continue the next line. And then jump while again back to the top. Test again. Because now T0 is 1. Is 1 is greater than 10? No. Repeat back again until it is 10. Now T0 is 10. Now we will check. If T0 10 is greater than, greater equal to T1, which is 10. Yes. Now branch will be taken. Now they will end the loop, right? Okay. Another version is that previously this is a loop just to count. Okay, just to count the looping. Now this time we will do some operation. So here we will sum is equal to sum plus I. So please correct the notes here. Now sum is equal to sum plus I here. Okay, so we need to use the I. Now, same thing, right? So, one is used for I, and then S0 is used for the sum. So first, you need to declare sum is 0. So S0 is 0, and then T1 is 0, 10, right? So T1 is initialized with 0 plus 10. So we will get 10. Now, set less than T3 as the flag. Okay. So is T0 less than T1? So true. True, So true. So T3 will become 1. So is 1 equal to 0? Then we will jump to N. Right? Now, they will need to jump to N if it's true. But no. T3 is contain 1. So 1 is not equal to 0. So continue with this next one. So here, for the sum, okay, because we are using the same sum is plus sum plus I, so scratch this and then you put it as dollar. Okay, what is your I? T0, so T0. So then we will get the I here lah. Same thing, Okay, now next is that once they add the sum, then we add the sentinel, we add the counter. I is equal to I plus 1. This is very important because of we need to update to ensure that the loop will end at one time, at the end of it, right? So T0, T0, 1. So now T0 become 1. And then we jump to the while back again and then test again. And then still T3 is 1, so we will not end. So we add the sum again until T0 is 10. Okay, now T0 is equal to T0 plus 1, and then at the end of it, it becomes 10. Now, when they jump to while, T0 is 10. Is it less than T1? No. Now, T3 becomes 0. So 0 in T3 is equal to register 0. Now we branch to N. Okay, so this is how we use the loop with some operations. Now, if you want to do some operation, the same thing as the C++, then do the same structure. 1, set a label for the looping here. and then test. Okay, test the looping or the condition so that it will be ended. So you will need this label to go to the end. And then within this loop, okay, you must have some counting. Okay, counting variable I here, counting variable to end the loop. So addr t0 t01, or maybe I minus minus. Okay, regardless, depends on your C++ coding, and then j while. Okay, so and then you jump to the while. So there is some branching that will go out of the while loop, right? Now for the second one, I've changed it and use a BGT. So instead of using the SLT and BEQ, now we combine it to become a BGT. Same thing. If I is less than 10, now you will use, okay, greater equal. So it's supposed to be BGE. Yeah. Supposed to be BGE. Okay. Now, if T0 is bigger than T1, then we will jump to the end. Now, if it tested if it's false, so we go to the next line. So S0, S0, T0, and then EDDI, T0, T01, and then we repeat 10 times. Now, 10, is it equal or bigger or equal to T1? Yes. Now we will branch to N. Thus, the loop will stop. Okay. So I have mentioned before, we have 5 addressing mode. Now, the fourth one is the PC relative addressing mode. The PC relative addressing mode is used in the conditional branch instruction. The core concept is that the program counter holds the address of the next instruction, which is the PC here. Okay. And then the branch target address is calculated based on the current PC. Okay. So based on the current PC, they will be added together with the offset. Offset. How many bytes? Okay. How many bytes? Okay. So in this case, in a 4 bytes, right? Multiple of 4 bytes. So the size is a 16-bit offset. So it can be a positive or negative. Then they will be sign extended into a 32 bits. Add it together with the current PC, then you will have the new PC. Thus, you will find the location. The branch destination is specified as an offset from the current instruction, enabling the position-independent code. Thus, the name is relative addressing because they depends on the current PC content. Okay. Now, in the example here, I have the while loops. While I is equal to 0, then we would sum is equal to sum plus I, and then I minus 1. Here, the count is minus 1, right? Okay, and then we will repeat back again until I is not equal to 0. Okay, so I is not equal to 0. Then um then they will stop. They will stop lah. Okay, so I think this is a mistake. I think uh oh sorry, betul betul, correct. I right now at the moment is a bigger, I is equal to 10. So is 10 equal to 0? No. So is 10 equal to 0? No, it's supposed to be exit, right? So let me correct back again. This one should be not equal. Not equal, So I not equal to 0. True. Then we will do the looping. Okay, so 10 will be minus 1, 10 times, okay, 10 times we will minus 1 until I become a 0. So now, is 0 not equal to 0, which is false? Then we will continue with the sum here, right? Now, in this case, okay, because we are using not equal, so we do the opposite. Okay, so BEQ is T1 equal to 0. Yes, then we will jump to finish, right? Now we want to look at this BEQ branch. So BEQ here, use the label finish. So where is the finish? Finish is on this line. Okay, look at the line. Okay, your PC is currently, the program counter is currently on this location. Okay, so how do they calculate the machine instruction? They look at the finish here, and then they look at the PC. Yeah. Okay, so when they are loaded up, okay, when they load the program, so the instruction address will be determined after that. So here the PC content is 0040008. Okay, and then to go to the finish, okay, they need to go 4 lines. Okay, the next one is a PC plus 4. Okay, we need to consider at this moment when the program has been determined, the PC were already loaded with PC plus 4, right? Then count line 1, line 2, and then line 3. Okay, and then all right, we will continue. So at the moment that the PC is at this instruction 0040008. So to count how many offset that we need to calculate. So the next line would be PC plus 4, and then we count line 1, line 2, and line 3. So here you will see the line 3. So that's your offset. How many lines do you need to go to branch to? Okay, and then next, because BEQ is under I-type instruction format, we will use the I-type. So BEQ T10 and then finish. Okay, in actual fact, if it's a only single line, you will not be able to change this into a machine instruction. You need a complete set of the instructions like this. Then you will be able to calculate how many lines do you need to branch to, right? Now here, finish means the label next to 3 lines that we need to branch. Okay, so finish is 3, and then 0 is register 0, and then T1 is register 9, and then we convert this into binary, so then you will get your machine instruction. Right, next is the pseudo direct addressing mode. Remember when we are using a if else and also the looping, we come across with the J type, right? The unconditional branch. So unconditional branch use pseudo direct addressing mode. Okay, primarily used for J type instruction, including J and jar. It contains 2 field, opcode and immediate. So the opcode is 6 bits and the immediate is 26 bit. So this immediate is what we call as the offset 26 bit for the jump target address. Okay, so the addressing is divided into 3. Okay, the first 4 upper bits comes from the upper 4 bits of the PC plus 4. Okay, so and then we combine it with the 26 bit um in the offset. Okay, in the offset, or from the current PC, yeah. And then sorry, not from the current PC, from the target address. Okay, so where is the label that we need to jump to, and then we find that original or the original address, okay, where we want to jump, and then we take the 26 bit. Okay, and then the rest of the 2 bits is always 00. Okay, it's a word align because one word is consists of 4 bytes. So 4 in a binary is 100. That's where the 00 comes from. Okay, now remember the J loop. Okay, here, where is the J loop? Here, this is the J loop. Okay, where is the loop? On this location. So we will take the 26 bit from this location. Okay, 0040008. Okay, and then for the J loop here, for this instruction, for this line instruction, we will look into the current PC 0040014. And then to jump to the 0040008. So remember that, now, right, so for this instruction, okay, we can do both sides, right? Okay, the address is taken from 0040008 here. Okay. Jump target address. The jump target address that we need to jump, the where the loop label is, where the loop that we need to go to. Right. So 0040008, and then you put it on, expand it into a binary form. Now this is what it looks like. And then take out the 26 bit. Okay, take out the 26 bit means that from this side, okay, so from this side until to this side, so this is your 26 bit, right? So as you can see here, I have grouped it 26 bit. So these 4 bits, 4 bits, 4 bits, now you will have 01000002. So this is what it looks like, in the um in the immediate offset. Okay, and then we put it there. You put it on the field offset, and then for the opcode for jump is 3. Okay, so when we convert it into machine code, so this is what it looks like. Okay, and then combine with the opcode 3. Now the command would be 0x0c10002. Okay, so it will be reversed. It can be reversed to get back again. Okay, so means that from this instruction, for example, if you have this instruction, okay, now convert this into binary. Convert this into binary. Okay, so convert this into binary. Okay, like this, such like this, and then, okay, put a 00 at the back because of what I have mentioned before. This one always word align 00. Okay, and then the front of it is the current PC. So the current PC is always starting on the within this time. So usually it will not exceed more than 50 lines. So usually it start with 000. So you can put a 000. Then you will get your uh, jump target address, the real jump target address. Okay. Okay, so instruction types. Okay. All J type instruction, J and JAL use a pseudo direct addressing because they are under J type. So J type is, all of them has a addressing mode. It's a sorry, use a pseudo direct addressing mode. But there's one, JR. Okay, JR is a jump register instruction. It's not categorized under J type but R type. It's a register base. So it is classified as R-type as it will direct the program to the 32-bit value stored in the register RS. The JR is mostly used to return back to the previous state or to the previous location. So you can also use the JRRE. Okay, most of the time the command used is JR jump register and then dollar register address. Okay, so most of the time they will use this command. Okay, in summary, this is the all the 5 that addressing mode that I have covered. Okay, for um for the instructions that has been covered so far, arithmetic, immediate, and then load and store word. Okay, and then we do have some branching and unconditional branching. Okay, so these are all the most basic commands that has been covered so far. Right, we will stop right now.